doesn't work. Okay. Okay, so I'm going to talk about.
Sorry, the Sufi is still on the.
Should I turn it off?
Yeah, but I guess I don't know if you want to.
I can keep it on as well.
No, I think people are not able to see. But Zeyu's.
Okay, I see. Okay.
Yeah. Just see the microphone.
Can they see now?
Yes. Yeah, that's good.
Okay, so I'm going to talk about rank extractors and related stuff. So this is joint work with Roshan Raj and Chong Shangguan, Zihan Zhang. So Roshan is also here. So the main objects I'll be looking at this talks about rank extractors. So rank condensers, rank extractors. These are basic objects in linear-algebraic pseudorandomness. So you can think of them as linear-algebraic analogs of randomness extractor and randomness condensers. And they have applications to theoretical computer science and problems like PIT and the construction of fine extractors over large fields and so on. And they're also connected to some other pseudorandom objects like subspace designs and something called strong blocking sets. These objects I will talk about later in this talk. In this talk, I'll only focus on the strong form of these objects called the lossless rank extractors, in the sense that as the linear maps, they the rank does not decrease. We don't lose anything, and also it's a rank extractor, meaning that it's surjective. Here let me give you the formal definition. So let F be a field, and let R and K be integers, R at most K. Consider a collection F of matrices, R by K matrices, E1 through En over F. And we say this collection is a KRL lossless rank extractor of size n if for any K by R matrix M of full rank R. The number of EIs in the collection such that the rank of EI times M is not equal to R is at most L. So meaning that for most EI in the collection multiply. So given M of rank R, if you multiply EI by M by EI, for most EI you still get a full rank R matrix. Okay, so this is for all except at most L matrices. Okay, and equivalently you can think of those matrices as linear maps from F to the K to F down to F to the R. So that means no matter what subspace of dimension R you look at, most of the linear maps restricting to that preserve the dimension, and this image is still R-dimensional, and the whole output as dimension R. Okay, so and for convenience, we also define a weaker object. Let's say F is KR lossless rank disperser. If we replace the condition that most EI works preserve the rank by the weaker condition that there is some EI that preserve the rank. This notion, I guess, is new. Somehow it's not taken, so we just call it a rank disperser because it's sort of like one-sided version of rank extractor. Okay. Okay, so now let's look at some existing constructions. So Gibson and Raz gave the first explicit construction for lossless rank extractors. So here's their construction. So you have a collection S of field elements. And for each alpha in S, there's an associated matrix E of E alpha. And its ijth entry is simply alpha to the I times j. Okay. And then they show that this is a KRL lossless rank extractor where L is KR squared. Okay. And then Forbes and Shpilka give a different construction. Similarly, for each alpha in S, there's an associated matrix E alpha. And Eij now is a little bit different. It's alpha to the j minus 1 times gamma to the j minus 1 to the I minus 1, where gamma is the field element. It's a non-zero element whose multiplicative order is at least k. And they show, this is actually in a later paper, the paper of Forbes, Sapshashi, and Shpilka. Their analysis shows that you can bound the number of bad matrices by R times K minus R. Okay. However, for these constructions, the one issue is that the field size needs to be large enough. In fact, to get a non-trivial result, it needs to be depend on the ambient space K and polynomially. Okay, so the natural question is, can we make the field size small and work over small field, but still get similar results? So, like, can we still get similar results over, say, when the field size is independent of K? Maybe maybe it can depend on R, or maybe it's just absolute constant. Right? Can we get a similar result? Not only is this a natural question, you'll see later, it has some applications to some combinatorial problem. Okay. So, you know, as you can guess, like a direct look, I mean, the original proof, like for example, for Spilka, doesn't directly work. And so let's take a look at why it doesn't work. So if you look at their proof, they consider symbolic matrix E, which is R by K matrix, defined this way. So ij's entry is x to the j minus 1 gamma to the j minus 1 to the I minus 1's power. And basically, you know, we want to show that for most alpha, E alpha times M still has full rank, right? And turns out this holds if and only if alpha is the non-root of the determinant of E times M. What it means is that to show that most alpha works, we just need to show determinant of E for M is a non-zero polynomial, because non-zero polynomial cannot have many roots, right? So it turns out the Forbes and Spilka, they did show this, and it follows that their construction does work as a lossless rank extractor. However, this does not work directly over small fields, because even though determinant of E times M is non-zero polynomial, you can just vanish every element in the field, right? The field is small, so you can, maybe not every element in the finite field is a root. So how do we fix this? A natural idea, if you know this algebraic geometry code, so it's based on so-called algebraic curves. So here we also use algebraic curves here. So instead of choosing a set of evaluation points from the field, which is small, we choose the evaluation points from an algebraic curve defined over FQ. So what is an algebraic curve? Algebraic curve is a one-dimensional variety. And the nice thing about it is that even though Q can be small, it can have a lot of points, evaluation points. Here, the evaluation points are what we call rational points, which roughly means the coordinates live in FQ. And there are examples of curves that have a lot of rational points. For example, when Q is a square, it's called a Van Hermitian curve. It's a Planck curve defined by this equation. You can check that it has Q to the 3/2 solutions. So number of rational points is Q to 3/2. This is larger than Q, but still polynomially related to Q. But it turns out you can consider more and more complicated curves where the number of rational points can be arbitrarily large compared with Q. Okay, and in this talk we'll be using so-called the projective curve, non-singular projective curves. Just want to say that these are geometric objects, but it turns out those projective curves correspond one-to-one to what we call function fields, or more precisely, function field, finitely generated function fields of transcendence degree 1. I would just call it function fields. So these are equivalent. You can use function field. Function fields is algebraic objects, and projective curves, these are geometric objects. But really, there is equivalence between the two. And the idea is to try to transfer the old proof, which use the fact that low-degree polynomials cannot have too many roots, to function field setting, right? But we need some a language for that. But it turns out it's doable, and in particular, this notion of a space of low-degree polynomials can be generalized, replaced by so-called Riemann-Roch space, associated with something called the divisor of degree D. I'm not going to define it, but you can think of it as an analog of low-degree polynomials. And it's behaved very similarly. For example, we know that low-degree polynomial of degree D can have no more than D roots. It turns out elements in L of D in the Riemann-Roch space can also cannot have more than D roots with multiplicity counted. So it's very similar. Okay, so we have a curve that have a lot of rational points, and low degree function not have many roots, right? So, but there must be some cost of using a curve. So what is the cost? The cost is that the dimension of the space of low degree functions does not behave like what we want, or the best we can hope. So if you look at the low degree polynomials, like the space of polynomials of degree at most d, it's exactly d plus 1, right? You have coefficients from 0 to d, so it's d plus 1 coefficients. However, if you look at the space of Riemann-Roch space associated with a low degree d divisor, it's only guaranteed that this dimension is between d plus 1 and d plus 1 minus g, where g is a non-negative integer called the genus of the curve or the function field. So, and this existence of this genus means if you do the similar kind of analysis, you introduce an error term. And to make sure you still get a meaningful result, you better hope this genus is small, right? So the conclusion is that we want explicit curves because we are interested in explicit constructions, and that has a lot of rational points, but at the same time, it should have a small genus. I wrote comparably, it should be comparatively small. This is the wrong word in English, but it means like it can be large, but it should be smaller compared with the non-rational points. Okay, and also mention that if you're familiar with the theory of algebraic geometry code, this is exactly the theory underlying algebraic geometry code. So it's classical theory, and algebraic geometry codes are generalized Reed-Solomon codes. But that being said, we are not really using algebraic geometry codes or any coding theory property as a black box. Instead, what we are doing is to look at the existing proof of analysis of lossless rank extractors and try to transfer this proof to the function field setting. So here's what we did. We define now S to be a set of evaluation points on the curve, and for each alpha in S, again, we associate the matrix E alpha. And this ijth entry is defined to be fj times gamma j to the s minus 1's power evaluated as alpha, where f1 to fk are, you can call it low degree functions. Those are the elements from the Riemann-Roch space. I've just called them low degree functions for simplicity, and they need to have distinct valuations at a distinguished point on the curve. And what are those gamma j? So gamma j is the jth element in this set, where we have g1 through gt. These are again low degree functions, and again their valuations are distinct at a distinguished point, and it should be decreasing in the decreasing order. So what are we doing here is the following. So if you look at the EI definition of E alpha ij, you ignore this fj, you look at the gamma j to the I minus 1. That's like a van der Waals matrix, right? So so what we want is to use the fact that the van der Waals determinant is non-zero even the elements are distinct. Right? This is also used in the Forbes-Brücke analysis, but that requires the elements to be distinct, right? In Forbes-Brücke construction, those elements are just the powers of some gamma. Gamma have large multiplicative order, but now the field is small. You cannot have distinct elements in the field, many distinct points, right? This field is small. So what we realized that is, okay, there's no need to insist using elements from the base field. We can use transcendental elements, right? So that's why we introduced those GIs. And so instead of considering power of some constant gamma, we use the set of elements of the form small power of gamma times some GI. So this gives you more elements. And then it turns out that by choosing this evaluation, by ordering it in this appropriate way, it's compatible. The use of GI doesn't screw the proof. It still works. And so so similar proof similar to Forbes and Brücke analysis still works. So this is a high-level idea, and then we need to choose the function field. As I said, you want the number of rational points to be large and the genus to be comparatively relatively small. And when Q is a square, it's well known there's a so-called the Garcia-Sticknaz tower. This is an explicit tower discovered in 1990s, like where explicit function field tower. If you go to look at larger and larger I, number of fractional points goes to infinity, and the genus also goes to infinity, but their quotient is at least the square root of q minus 1. This is in fact optimal. And we can use this. And when q is not a square, when q is a non-prime and not a square, we can use another tower. This is discovered more recently in 2015, called Balsa-Biden-Garcia-Sticknot tower, which has weaker but similar performance. And then we use that one. And combining the two cases, this is one of our main theorem. So for non-prime q, q being polynomially large enough polynomially in R, for infinite many k, there exists explicit KRL lossless extractor of size n, and L is big O bounded by the number of bad matrices is bounded by big O of R times k minus R. So that matches the same bounding for up to constant factor. But note that here's for infinite many k. This is like if you know that for algebraic object code, similarly is also for like infinite many code lengths. Here is for infinite many k, but you can replace it by for all k, except that we would have to increase L by some other factor that depends polynomially on q. Okay, right. But note that this is for non-prime q. The problem for prime q is that we don't have such nice explicit functional towers. We do know, so there's a result of Sarah show that for prime q and in fact for arbitrary q, there exist function field towers where they can lower bound the quotient by omega log of q. Okay, but unfortunately we cannot use that. The most serious problem of this is the reason we cannot use it is that we use the tool called class field towers, and that is not explicit. And we are interested only in explicit constructions. Okay, so they cannot use this, unfortunately. But you know, these tools can still be used for other places. You know, you probably have heard that the recent result of OpenAI, where they get this disproof that give a lot of people existential crisis, and that they consider number field instead of function field, but they also use class field towers there. But because we're only interested in explicit construction, we cannot use this. Nevertheless, you'll see soon that there's a workaround that we can address the prime field to some extent. And this workaround is based on a technique which we call field reduction. So idea is following, suppose we have an extension field, f capital Q over f little q, let's say of degree d, and the E1 through ED is the basis or a small field. Now suppose we have a, let's say, lossless rank extractor or disperser over this extension field. Can we turn it into a 1 over the small field, right? Turns out we can. And the idea is very simple. This is the basic construction. You can you look at the matrices over the extension field. You look at their rows, there's a vectors, and basically it's possible to decompose V into a sum of vectors V1 through Vd over a small field multiplied by the scalars Ei. And then we simply replace V by each of these Vi's. That gives matrix. If you do this row by row for every matrix, it gives new matrices over small field. Of course, it would increase the size of the number of matrices by a large factor. In fact, by a factor of d to the r. But still, we get we have this theorem that says, starting from explicit lossless rank disperser over f capital Q can be turned into a new one over small field, and size increased by a factor d to the r. So as a kind of application, if you are interested in constructing over, say, f2, you can use the main theorem on the previous slide to construct over the field of size polynomial in R, and then apply this theorem to get disperser or rank disperser of f2. Right? Now, if your f little q is already large enough, in fact, there is a more sophisticated way of doing it, an improvement. The idea is that instead of replacing V by each of the Vi, you can replace it by some pseudo-random linear combinations of the Vi. And also for different rows, instead of choosing those linear combinations independently, maybe you can choose them in a correlated way, right? So the question is, how do we choose those linear combinations? It turns out the question of choosing those good linear combinations reduces to a PIT problem. So we want to hit some polynomial, and this polynomial has a structure. It's a determinant of some symbolic matrix A, and A is the sum of variable xi multiplied by AI, and AI are rank 1 matrices. Now those polynomials are known to have quasi-polynomial sets for this sets. Thanks to the nice result of Gurdjieff and Siraf, they solved it by reducing it to PIT for neutrality intersection, and further construct a quasi-polynomial hidden set for those polynomials. And we use a variant of their construction. So as a result, as a consequence, if your Q is already polynomially large, not in the ambient space, but in D and R, then you can turn the explicit lossless rank extractor into a one over small field where the number L and N only increase by a quasi-polynomial factor instead of exponential factor, ER. And as an application of this, you can now go back to address the prime field case, which is annoying, but what you can do is you start from prime field, but you can take a quadratic extension, right? And then it's no longer prime field, and then you construct the lossless rank extractor there, and then you apply this theorem. So you obtain the lossless rank extractor with this loss, but to some extent is addressed. Okay, so finally, I want to talk about some connections to other pseudorandom objects. First one is the subspace design. So subspace design, an RL subspace design is basically a collection of subspaces in F to the K. There are two notions: weak subspace design and strong subspace design. So what we want is the following. So for weak subspace design, what we want is for any dimension R subspace W, the number of VI is such that the intersection between V and W has positive dimensions at most L. And for strong subspace design, it's a stronger condition. It says not only that, but the total sum of the dimension is bounded by L. Okay, and Forbes and Goswami has a paper that discusses all these various definitions in linear-algebraic pseudorandomness. But basically, for us, the lossless rank extractors defined in this slide essentially is equivalent to weak subspace designs consisting of codimension R subspaces. So, and we have a construction of lossless rank extractors of small fields, so can just use this equivalence to turn them into a statement about weak subspace designs. So here I only stated for large enough non-prime Q, but you can also state for prime field and absolute constant sized field. But I just want to point out that the result we get only gives you weak subspace design. They don't give you strong subspace design. And strong subspace design receive a lot of interest in recent years because people realize they have connections to algebraic error cutting codes that have very strong listed decodability. Goswami and Kopati, they use Fourier-Real code and universal multiplicity code to give very good strong subspace designs, but they require the field size to be large, polynomially large in K, and there's no matching result when Q is independent of K. And unfortunately, our technique doesn't apply. I just want to say really why it doesn't apply. And my understanding is that basically you need some actual property about the matrix E. Some structure properties. There's a related paper here by Bandari, Harsha, Kumasuda. They consider list decodability. They formulate some properties, like some linear, what they call linear operator property, that explains why codes have capacity achieving list decodable property. Now here is we consider subspace design property, but it's similar, strong subspace design property, but it's very closely related. So we need some structure like in our paper, but the construction in our paper doesn't have such properties. Of course, you can try to design the matrix E to have those properties, but the problem is if you do that, then it becomes more difficult to prove the polynomial to be non-zero. Like you recall that we want to determine the E times M to be non-zero. Our design of E is done in this way that it facilitates the proof that the proving the non-zeroness is easy. As a consequence, the doesn't have the property. Now, if you insist the property, then it becomes harder to have non-zero means property. So we don't know how to get both. That's the reason we don't get strong subset designs. But there do exist weaker results on explicit subset designs. One is by Goswami and Xing and Yuan. They also use function fields, but different function fields. They consider the matrices that have such kind of properties, but they only get some weaker parameters. And there's a more recent paper by Gaio and Goswami and Xie. They use like expander, the AEL construction from coding theory to also get some strong subset designs with suboptimal parameters. Okay, so another object I want to discuss is strong blocking sets. This is an object that some combinatorialists study. So what is strong blocking sets? So a subset B in the k-1 dimensional projective space over field F is called a strong S blocking set, where S is an integer. If for any codimension S projective subspace V, the intersection B intersect V spans V, meaning that V is the smallest projective subspace containing B intersect V. So it's a pseudo-random property. It just means the intersection like spreads all over the place, so it will span V. And so this has been studied a lot by combinatorialists, and also in discrete geometry, and also in strong one block sets are known to be equivalent to something called encoding theory called minimal linear codes. So its connection to a rank constructor can be shown by this lemma. In fact, its connection to rank dispersers. So if F is a ks plus 1L lossless rank disperser, what we can do is to take those matrices, look at their row spaces, which give a bunch of subspaces, and then look at the projective subspaces, associated projective subspaces, and then you just take the union. And the lemma says this is a strong S blocking set. Now we have a explicit construction of lossless rank dispersers, not only just over even over F2, right? So we can just plug in to get strong blocking sets. And this is a corollary for like a Q being polynomial in R. But you can also state it for small q, constant prime q and a constant q, which would increase the size by some either cosine polynomial factor or exponential factor. And in the case, even in the case of s equal to 1, we could recover result which was only proved recently by Alon et al. And they show that you exist strong one blocking set matching the optimal size, but it's a different construction. We use the expander graph plus algebraic geometry codes, and we use this function field without the expander graphs. And finally, there's also different construction which use in our paper, which use absolute bias sets. It's completely different, so I guess I'll just skip it. But this turns out to be the better one if Q is small. But if Q is large, the one I just described is a better one. With some open problems, can we get better construction or strong subspace design? And even when Q is constant, can we lose something less than exponential? Can we get a sub-exponential loss in the size? And finally, our constant size fields, we use this field reduction to get a lossless rank dispersal over constant size field, but it reduces the fraction of good matrices exponentially. Can we do better? In fact, non-explicitly, we know that there exists constant construction in which constant fraction of matrices are good, but right now we only know exponential fraction of the matrices are good. So there's a huge gap. Okay, thank you.
Any questions?
So what kind of parameters are we looking for in strong subspace design?
Yeah, it's originally in the slides, but I removed it. It's a similar, basically, you look at the statement for weak and then just replace weak by strong. It's not like that, but actually, Goswami and Kopati, they put a much more general statement. You can check. Yeah.